All right, so our next up, we are again working with our motion equations. But I talked in the last class about sometimes there's hidden elements, hidden variables within a question. This is the most common hidden element, and that is the acceleration due to gravity. Now, if you had an opportunity, I hope you did, to watch those two videos. One, just to kind of recap, is an old school video. I believe it was from 1973 or 1974. Where they looked at the fact that if you dropped two items, and specifically look at a feather and I believe it was a hammer, and they dropped them at the same, they fall at the same rate. The acceleration due to gravity on the moon is the same. And so it doesn't matter how big the object, how heavy it is, what it looks like, because there's no air on the moon, the objects will drop on the ground at the same time. Now, the other video, which is actually new to me, is that they created space on Earth, which means there is no air. There is just space, hence the name. So there's nothing there. And so they recreated that experiment where they dropped those two objects, a feather and I can't remember now, I believe it was a bowling ball. And again, they landed at the same time. And that is because the acceleration due to gravity on any planet is the same as long as there's no air. So the objects will accelerate, whether it's a feather or whether it's a rock, they will drop at the same rate, or accelerate at the same rate as long as there's no air. Now, different planets actually have different accelerations due to gravity. On Earth, our acceleration due to gravity, which is called G for gravity, is 9.8 meters per second squared, and it is a vector. Hopefully I don't have to tell you which direction gravity works in, but it does, in case you're wondering, it works down. All right, now some things that can change the acceleration of gravity that kind of maybe not, you realize that this could happen with the bowling ball and the feather, is air. So a feather will attract more air than a hammer will be, or the air will have more of an effect on the feather for various reasons, mass and its surface area. And so that feather gets slowed down by the air, where the hammer, which has a much greater mass and a smaller surface area, will keep falling and cut through the air more so. But if, again, you do not have any air at all, the objects will land at the same time, which is really weird. Now, I can remember being a kid on the CN Tower, and one of the stories was if you threw a penny off the CN Tower, and unfortunately, I'm old enough to have done that. You can't do it anymore, but I have thrown a penny off the CN Tower. Somebody would always say, well, don't do that, because if it lands on somebody's head, it will kill them because it would speed up so fast. And in fact, that's not true at all. Or I heard the penny would go into the cement, into the sidewalk. And in fact, that's not true at all, because what happens is eventually the penny, which isn't very heavy and has a relatively good surface area, the air catches it and pushes it back up so that it stops speeding up at the same rate. And that's why you wouldn't get hurt by a penny if somebody threw it off the CN Tower. But for all intents and purposes, for what we're doing, we're on space. There's no air. We're not talking about air resistance, okay? So I want to keep that in mind. But there is our acceleration due to gravity. Again, that's a secret thing that's happening on. You can't see it, but it's there. And our rate is 9.8 meters per second squared, as long as you're close to Earth's surface, within a kilometer, somewhere in there, which obviously we are from all these questions. All right, so again, I'm going to go through my motion questions. Again, these are with the secret value here. And I'm going to show you some different, again, the same steps going through the motion questions, but some little tricks that can happen. So I get to example one. Again, I'm going to follow the same format I did earlier this morning. So a Major League Baseball pitcher throws a baseball straight up into the air, and the ball travels for 4 seconds, reaching a height of 52 meters. Good throw. Before returning to the pitcher's hand exactly at the height he released it. With what velocity does the baseball strike the pitcher's hand on the way back down? All right, so there we go. So ball player is throwing this ball straight up in the air, catches it. We want to know what velocity it is going to actually hit the player's hand at, excluding air again. All right, so I've read the question. I understand what's going on. Now I'm going to get the information from it. So a Major League Baseball pitcher throws the ball straight up into the air, and the ball travels for 4 seconds. So I'm going to throw that down. Delta T is 4 seconds. All right. Now it reaches a height of 52 meters before traveling back down to the pitcher's hand. So the weird thing here is that our delta D, which is our displacement, right? And again, this is the difference between distance and displacement, is the distance is, this thing goes 52 up, 52 back. So our distance is 104 meters, but I'm looking for displacement, and displacement is all about where you, it's a direction and magnitude from where you start to where you finish. Well, if I throw the ball up, it goes 52 up and 52 back and ends up back in my hand. In the end, it didn't go anywhere because the starting position and the finishing position are the same. So a little bit of secret information here in the question. All right, and what we want to know is, what is the final velocity when it strikes the hand? Now, again, the acceleration, the reason this ball is coming back down is gravity. And so that ball is constantly being accelerated at a rate of 9.8 meters per second squared. And of course, down. All right, so again, there's our information. Couple secret pieces here. Again, the acceleration due to gravity and also our displacement. So now I get to my equation sheet and figuring out which equation I'm going to use. So again, the steps are, I need the equation with VF in it, and then I need to know everything else in that equation. So I look at my first equation. It does have a VF in it, but I don't have delta T, so I can't use the first equation. The second equation doesn't even have VF. Gone, I'm not using it. My third equation has a VF in it, but I don't have VI, so I can't use it. The fourth equation, we have the VF in it, but again, no VI. So I can't use that one. So hopefully I am here with my last equation, which has a VF. I need a delta D, got it. I need a delta T, got it. I need an acceleration, I got it. There we go. Our last equation there in the chart. So I'm going to write it down. We have delta D is equal to VF times delta T minus 1/2 A delta T squared. All right, so now I'm going to substitute into my equation. Now, again, you can use your directions, or you can denote your directions or specify your directions any way you want, but I typically will stay the same 99.9% of the time. I go up as positive, down as negative. All right, so in this case, putting in the displacement, we don't have an up or down, it's just 0, same spot. I have my VF. My delta T is 4, so I substitute that in there. Again, the fraction, I'm going to convert that to a decimal. There it is, 0.5. My acceleration is 9.8, but it is in the direction of down, clearly, because it's gravity. So I put in a negative 9.8 here. And again, my T squared, T is 4, so I'm going to have a 4 squared there. All right, so now I've substituted into my equation. I've accounted for the signs and the directions. All right, so now it's just solving here. So let's see here. VF times 4, well, mostly in math, you have the numerical coefficient in front, so 4 times VF. Again, I'm going to do bedness here. So I got my minus 0.5 times my minus 9.8. 4 squared is 16. All right. Again, I can simplify here by multiplying those numbers. All right, so I still got this 4 times VF here. Let's see here. I got a negative times a negative. Going to give me a positive. Times a positive gives me a positive. So I multiply those 4 numbers, and I get plus 78.4. All right, I got to get VF by itself, so I'm going to move that 78.4 over to the other side. It changes sides, it changes sign. All right, now let's get VF by itself. So I'm going to divide both sides by 4 here. And let's see here, VF is equal to, I take negative 78.4 divided by 4, and I get negative 19.6. All right, but again, I'm not done yet. I got to express VF as a vector because it is with magnitude and direction, and I got to put my units in there. All right, so VF is equal to, well, the magnitude is 19.6. If you look at our units, our distance is in meters, our time's in seconds, so our velocity is in meters per second. And see the negative sign. That tells me my direction is down. And there we go. So the final velocity is this baseball would hit my hand, or the pitcher's hand, because I can't throw it that far, 19.6 meters per second down would be our final velocity. All right, so let's try another one of those. All right, so example number 2, all about a cannonball, I believe. All right, so here we go. Let's see what we got here. A cannonball is shot straight up into the air. I don't think that's a smart idea. I don't recommend it. With an initial velocity of 25 meters per second up, hence straight up in the air. What is the maximum height of the cannonball? Okay, so this is a little bit different again. So again, I read the question. So I'm going to extract the information and then figure out what the heck I'm looking for, okay? So here we go. A cannonball straight up into the air with initial velocity of 25 meters per second. All right, so I'm going to write that down. There's our VI. And it is 25 meters per second up, on its way up. All right, now again, because this cannonball shot straight up, I know what the rate of acceleration is because the only thing acting on it is gravity. And so the acceleration for this cannonball is 9.8 meters per second squared down. Now, because my initial velocity is up and my acceleration is down, well, that means it's decelerating. But again, in physics, we just talked about it, it's accelerating in the opposite direction, slowing down. And in fact, gravity will continually slow it down until it gets to its maximum height. And that is what we're going to figure out is the displacement when it gets to its maximum height. All right, so that's height, displacement. How far up will it go before it stops, right? When it gets to its maximum height, it goes up and up and up. It's slowing down. And then at the maximum height, it stops. So I want to know the spot where it stops. Again, secret variable. So that means our VF is equal to 0. All right, so, and then after that, it starts accelerating downwards at a rate of 9.8 meters per second squared, downwards. All right, so now I've got my variables, right? I got all these here. So now again, I'm going to my equation sheet, seeing what formula I'm going to use. Got to have a delta D in it. And then I got to know everything else in the equation. So again, I look at my first equation. There's not even a delta D. Can't use it. My second equation, it does have a delta D. I got a VI. I don't have delta T. Can't use the second equation. The third equation, same thing. I don't have delta T. All right. I get to the fourth equation. I need VF. I need delta D in it. I do. I need VF. I got it. I need VI. And I need A. Okay. Fourth equation I'm going to use, which is, again, VF squared is equal to VI squared plus 2A delta D. All right. So, again, I'm going to now substitute in, accounting for my signs. Again, I always 99.9. Up is positive, down is negative. All right, so my VF, well, it doesn't matter. It is 0. So I have a 0 squared there. All right, my VI, it's up, so it's a positive 25. So I put a positive 25 in here and I square it. Plus 2 times A. A is 9.8, but it's down. So I'm going to put in a negative 9.8 there. And I've got my delta D. All right. So just simplifying now and solving. So, well, 0 squared is 0. 25 squared, that's going to be a calculator thing for me. I think it's 625, given my math knowledge. It is 625. All right, positive times a negative. I'm going to have a negative number in front there. So 2 times negative 9.8 is negative 19.6 delta D. All right, so again, solving, I'm going to move this negative 19.6 delta D over to the other side. So that means it's going to become a positive 19.6 times delta D, which again is equal to my 625 that's over there. All right, and again, the whole idea here is I'm getting delta D by itself, so I'm going to divide by my numerical coefficient here on both sides. And my delta D, let's see here, we're going to put some units and direction on it here. My displacement, I take 625, I divide it by, I get 31.89. All right, my displacement here, what's the maximum height? Meters, it's positive, and so this ball goes 31.89 meters. Oh, no, ball cannonball goes up 31.89 meters. All right, so again, there's a little few secret variables in there when you're talking about the displacement there, because it goes up, comes back down, lands in the same spot, so it, in the end, it didn't go anywhere from its resting first position to its final position. All right, let's example 3. Which I believe is a two-parter. Two-parter, example 3. All right, so let's have a look here. What do we got? All right, so look here. A tennis player lobs a tennis ball up in the air during a serve, okay, at a rate of 3 meters per second. What is the maximum height of the tennis ball? Okay, we just had this type of question. All right, so again, this person, when I look at it, tennis player lobs the ball up at a rate of 3 meters per second. So again, there's our VI. Is 3 meters per second, and of course up when you're doing a serve in tennis. All right, and again, because the only thing acting on that ball is gravity, our acceleration for that ball has to be 9.8 meters per second squared, and of course the direction of gravity is down. All right, now again, when you're at your maximum height, when anything's going up, not anything, teaching physics, but when most things go up, they come down. And so it goes up, 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 reaches its maximum height where it absolutely stops. And then its velocity begins to become moving downwards. All right. But at the very maximum height, our VF is 0. And again, we are looking for our delta D. How far up does it go? All right. So let's check it out. So this one's a little bit different because we have different variables. But I am going to go to my question sheet. This time again, we're looking for delta D, and so we have to know this information here. It's different than what we knew before, I think. All right, so I look at my first equation. I don't have a delta. Looking for delta D, it doesn't even have it in the equation. The second equation has delta D, but no delta T. We don't have delta T. Third equation, there is a delta D there, but again, we're missing delta T. Fourth equation, that's what we used last time. We have delta D in it. We need VF, okay. We need VI, and we need A. Perfect. So it looks like we're going to use VF squared is equal to VI squared plus 2 times A delta D. All right. So once again, I'm going to substitute in, same way I did before. So let's see here, VF 0. All right, my VI is 3 and it's up. So again, I'm going to put a positive 3 in there and square it. Plus 2 times our A, which again is 9.8, down. So I'm going to put in a negative 9.8 here, times my delta D. All right, so again, just simplifying here. So I have 0 squared, which is 0. 3 squared is 9. And then let's see, 2 times negative 9.8 is going to be negative 19.6 again, times my delta D. All right, so it's just like last time out. So I'm going to move that negative 19.6 delta D over to the other side. It equals 9. All right, let's see what else we got. All right, finally get delta D by itself. So I divide both sides by delta D, or by 19.6, sorry, to find delta D. And our delta D is going to be, let's see here, 9 divided by 19.6. That's not very high. Well, I guess it's a tennis ball, right? I get 0.48 meters. And of course, because it's positive, our displacement is up for a tennis ball. So it's going up about 50 centimeters. Yeah, makes sense. All right, so that is A. Now I'm going to write down delta D here. Let's get rid of this question mark. And I'm going to put in my 0.48 meters up. All right. So there we go. We have our displacement, but then I get to B, where it says, how long will it take the tennis ball to reach its maximum height? So how long? So I'm looking for my delta T. So I'm going to get rid of this info here. Better spray it first. Like a smart board. All right. So there's my information still, because we're on the same question. I'm going to leave it. So again, I'm looking at how long will it take the tennis ball to reach its maximum height. All right, so now I got another piece of information here. So I'm going to go to, again, my equation sheet, see what I'm looking for, if I can find the equation I'm looking for. And so let's see, I need delta T. So I go to my first equation. It's got a delta T in it, but I need A. Got it. I need a VF. Got it. And I need a VI. Got it. All right. Looks like I'm going to use my first equation, which is A is equal to VF minus VI and divided by my delta T over there. All right. So I'm going to substitute in, again, accounting for my signs, which again, I've said many times, 99% of the time, up's positive, down's negative. All right. So my acceleration here, 9.8, but it is down. So we have a negative 9.8. Over the other side, my VF is 0. Subtract. And let's see here, VI, 3 meters per second, but it's up. So the 3 stays positive. All right, so that negative sign there is because of, that's part of the equation, not from the 3. And I have my delta T down below here. All right, now I'm just going to rewrite this a little bit, not doing anything crazy here. Just the top here, 0 minus 3 is a negative 3. Now, this is tough because I got a delta T in the denominator, but here's a trick I use in math a lot and in physics. I create a fraction equaling a fraction. And to do that, I can just take any number divided by 1 to create a fraction, because any number divided by a 1 is the same number. So I'm not changing the number, just changing the way it looks by making it a fraction. The reason I make a fraction equaling a fraction is so I can cross multiply and just totally get rid of fractions. So in this case, I have 1 times negative 3. Well, let's go this way. I have negative 9.8 times delta T when I cross multiply. And that's going to be equal to 1 times negative 3, which is a negative 3. All right, and I'm going to now divide by my numerical coefficient here, which is negative 9.8. And so my delta t, let's see, I have -3 divided by -9.8. That's going to be a decimal. And let's see, what do we get here? 0.31 seconds is how long it takes that tennis ball, to get to its maximum height, which is just less than 50 centimeters, 0.48 meters, so 48 centimeters. Again, something to watch out for in this question. If you happen to get a time that is negative, that's something, you mess something up. All right, that's something to watch out for. Time can't be negative. That's something we will go over as we get along, but if you can't go back in time. So something to watch out for to see if you made a mistake. Sometimes your answers come out and you can't tell if you made a mistake, but with time you can, because if it is negative, you messed up a sign somewhere, or you put the wrong value into the equation somewhere along the line. Something bad happened. All right, so that's just a little tip. But that is acceleration due to gravity. Again, using our motion